Welcome to our channel, and today we are going to help you understand the paper GeoDream, disentangling 2D and geometric priors for high fidelity and consistent 3D generation. The current paper presents an advancement over previous works in the field of 3D content generation from textual descriptions. Previous papers have tackled various aspects of this task. However, they encounter issues such as geometric and color inconsistencies across different views. Paper 2309.0453, Difficulties in Generating Multiple Representations of 3D Assets Efficiently, Paper 2305.02463, Slow Optimization Processes in 3D Content Creation, Paper 2309.1653, The Need for Improvements in Multi-View Consistency, Paper 22310.1343, and the challenge of 3D synthesis without large-scale labeled 3D data or efficient 3D denoising architectures, paper 2209.1498. The current paper introduces GeoDream, which significantly improves upon these earlier efforts by using a novel approach that merges 2D diffusion models and 3D geometric priors. GeoDream addresses the Janus problems, inconsistencies in 3D geometric structures, and artifacts present in earlier models by explicitly incorporating generalized 3D priors to maintain spatial consistency. This method first generates multi-view images with a diffusion model and then constructs a cost volume for native 3D geometric priors, ensuring consistency in 3D space. A disentangled design refines these 3D priors and enhances 3D awareness in the 2D diffusion model for better guidance and more accurate refinements, leading to more semantically coherent textured meshes. In summary, GeoDream outperforms previous methods by producing more 3D consistent and high-fidelity textured meshes while maintaining diverse and realistic renderings at high resolutions. It successfully combines 3D geometry and 2D diffusion processes to create superior quality 3D models from textual descriptions. The text discusses GeoDream, a novel method for generating high-fidelity and consistent 3D structures from text descriptions. Traditional text-to-image diffusion models perform well for 2D image synthesis but struggle when converting 2D images to 3D due to a lack of 3D awareness, resulting in geometric inconsistencies and artifacts in the generated 3D objects. GeoDream addresses these issues by incorporating generalized 3D priors into the 2D diffusion models. The process begins with generating posed images using a multi-view diffusion model, followed by constructing a cost volume from these images that acts as a 3D geometric prior. This ensures spatial consistency in the 3D space. The method further utilizes 3D geometric priors to enhance the 3D awareness of the 2D diffusion models through a disentangled design, which allows for the refinement of both the 2D and 3D priors. This refinement aids in creating more realistic and semantically coherent 3D textured meshes. With high-resolution renderings, the effectiveness of GeoDream is demonstrated through numerical and visual comparisons, which show that it generates better 3D consistency compared to other methods, with realistic renderings up to 1:24 × 10^24 resolution. The authors also note that while learning from 3D datasets is theoretically correct, 3D data is expensive and scarce. Nevertheless, recent works fine-tune pre-trained 2D diffusion models using limited 3D data to overcome these challenges, and GeoDream represents an advancement in this area. The authors mention their affiliation with various institutions, and the code and 3D metric evaluation are made available for others to access and utilize. Please note that this summary is based on the abstract and the introduction of the text provided. A complete understanding of the text would require further details and context that are not included in the excerpt. The text summarizes a collection of images and briefly mentions a technology known as GeoDream. The images include 1. Textured meshes, an astronaut riding a horse in a style reminiscent of Wes Anderson, a highly detailed and colored rendering of a super cute red panda engrossed in reading a book, a vibrantly illustrated toucan with a large beak, a flamingo standing on one leg in shallow water, a high-quality image of a dragon, an appetizing creamy lemon cake, a carving of a bald eagle made from wood. 2. Rendered images, a professional quality photograph of a chocolate brownie dessert accompanied by ice cream. Lastly, The technology called GeoDream is discussed very briefly. GeoDream is described as a solution to the Janus problems by combining 3D modeling techniques with 2D image enhancements to produce consistent multi-view rendered images and well-detailed textured meshes. The rendering process includes the removal of the background for better visual clarity. The provided text discusses a computational technique called GeoDream, a novel method meant to generate high-quality, consistent 3D structures from 2D image predictions. Traditional methods often struggle with oversmoothing and losing semantic geometry when dealing with imaginative or uncommon scenes beyond the training data distribution. GeoDream aims to overcome these issues by introducing explicit generalized 3D priors in combination with 2D diffusion priors, thereby enhancing the capacity to generate clear, consistent 3D geometric structures without compromising diversity and fidelity. Key innovations of GeoDream include 1. The use of 3D native priors within the 3D world space to handle inconsistencies stemming from multi-view predicted priors and varying camera viewpoints. The disentanglement of 3D and 2D priors, leveraging the strengths of each to maintain generalization and preserve consistency. GeoDream approaches the generation process by reconstructing a cost volume as native 3D priors from the aggregation of predicted multi-view 2D images in 3D space. This method benefits from the robust and general nature of such aggregation operations, commonly found in multi-view stereo (MVS) techniques. Extensive experiments demonstrate that GeoDream's 3D priors adapt well to various multi-view diffusion models, and the introduction of a viewpoint sampling strategy enhances the stability of the 3D priors. GeoDream also explores a disentangled design, where geometric clues provided by 3D priors unleash the potential of 3D awareness in 2D diffusion priors without compromising 2D prior advantages like generalization and creativity. The resulting 3D assets from GeoDream have been shown to possess plausible geometry and detailed rendering quality, aided by refined 3D priors which inform the evolution of 2D priors. The method successfully increases rendering resolution from 512 to 1024. Theorizing that the improved geometry and texture provided by 3D priors simplify the optimization due to their closeness to diffuse distributions. Finally, GeoDream introduced a new metric, Uni3D score, for evaluating semantic coherence in 3D, and comparisons with other methods demonstrated GeoDream's superior ability to produce high-resolution images and textured meshes while addressing the Janus problems related to consistent appearance from different viewpoints. The text discusses advancements in the creation of 3D content by combining 2D and 3D generative models. Traditional models like GANs and VAEs have been supplemented with diffusion models to improve the generation of diverse 3D objects. Recent techniques attempt to enhance 3D generation by utilizing strong 2D diffusion priors in conjunction with 3D representations such as NeRF, DMTNet, or NUIS. This approach mitigates the need for extensive 3D datasets by using various techniques like score distillation sampling schedules and losses specifically designed for refining 3D representations. However, these methods often suffer from 3D consistency issues due to the reliance on 2D models for training. Some methods aim to address these issues by tweaking score functions or using negative prompts, but 3D consistency remains a challenge. To overcome these limitations, the authors propose the use of explicit 3D priors in combination with 2D priors to achieve more detailed and consistent 3D generation. The authors mention various latent diffusion models trained on 3D data and efforts by OpenAI to directly generate 3D shapes. However, generalizability remains unproven due to the scarcity of 3D data. The release of large-scale 3D datasets like Objaverse has led to attempts to fine-tune 2D diffusion models for multi-view image generation from 3D data, utilizing consistency clues to infer 3D information. The text describes a method called GeoDream, which incorporates explicit 3D priors with 2D diffusion priors to ensure 3D consistency and decouple geometric and texture information for optimization. GeoDream stages include training 3D priors to encode geometry and appearance, and refining these priors through a 2D diffusion model to enhance rendering quality and geometric accuracy. The method aims to generate 3D content with accurate geometry and detailed visual representation. The given text describes a method for generating 3D models from multi-view images using a process that involves constructing a cost volume for voxel neural features and decoding both geometry and texture details. Summary. The process starts by extracting 2D feature maps from multiple images using a 2D feature network. A volume reconstruction model takes these maps and produces a cost volume where each voxel's neural feature is computed by projecting its location onto image feature planes and calculating the variance of these features. This cost volume is then processed by a sparse 3D CNN to create a refined cost volume. The cost volume is decoded into geometry, represented by signed distance function, SDF values, and texture, using different multi-layer perceptrons, MLP decoders, for geometry and texture. The final image is rendered using SDF-based volume rendering, taking pre-trained parameters from a model trained on true images. The method includes a priors refinement stage, where geometric priors obtained in a training stage are fine-tuned with 2D diffusion priors. The method uses predictions from various multi-view diffusion models and a critical viewpoint sampling strategy to ensure robust adaptation to different models, enhancing 3D generation while maintaining generalization and creativity from 2D diffusion. For generating multi-view images, predefined camera poses and user-provided conditions are used to predict posed images and extract their 2D feature maps. These feature maps replace the earlier ones to recalculate a value analogous to the SDF at query points, serving as geometric priors. To avoid restricting textures to the styles of a training dataset, the pre-trained texture priors are dropped. Instead, an efficient, high-resolution texture encoding method is used, and a learnable hash encoding decodes colors at arbitrary query points. Finally, to integrate 3D geometric priors with 2D diffusion priors, a VSD loss is minimized. This approach, called GeoDream, aims to unlock the potential of 3D awareness within a 2D diffusion model and avoid producing generic views, thereby creating better 3D assets. The text discusses the optimization of 3D representations generated from textual descriptions using various methods. The process involves refining the parameters, Tat1, Theta2, 3, of different parts of the system, the cost volume, the hash encoding, and the texture decoder. Camera poses are sampled, and 2D images are rendered using differential rendering. The goal is to minimize the VSD loss by adjusting these parameters, guided by a pre-trained diffusion model and a trainable diffusion model. The team uses a learning rate decay strategy to preserve geometric cues and focuses on details in the early optimization stages. For high-resolution rendering, they utilize DMTET to extract textured 3D meshes from NUS, and, following Prolific Dreamer's method, they optimize geometry and texture separately. The authors report on their model's performance against existing methods by highlighting their approach's unique advantage in inferring 3D geometry and reducing artifacts with the aid of explicit 3D priors. They collected 35 textual prompts and rendered images for comparison, using metrics like EVD clip for image fidelity and clip R-score for semantic coherence. They also propose adopting Uni3D score for 3D semantic consistency assessment. Significantly, the methods they compare against include Dream Fusion, Prolific Dreamer, MV-Dream, GS-Gen, Fantasia 3D, and Wonder 3D. The text hints at the challenge of applying traditional 3D reconstruction assessment metrics to text-to-3D tasks due to the lack of ground truth, noting the need for subjective metrics. In overall, the focus revolves around improving the generation of 3D models from text prompts, assessing these models through various metrics, and highlighting the difficulties and novel approaches in text-to-3D tasks without ground truth benchmarks. The text discusses the performance of different methods used to generate 3D images and meshes from textual descriptions. Specifically, it compares 4 models: Dream Fusion, Prolific Dreamer, MV-Dream, and the author's method, presumably referred to as ours. The comparison is based on both qualitative and quantitative metrics. Qualitative comparison. The provided Figure 3 illustrates the visual differences between the models. For non-symmetric geometries, the front, side, and back views are shown. The back views are marked with red rectangles to emphasize issues with creating multiple faces. Dream Fusion and Prolific Dreamer are capable of generating high-quality frontal views, but fail to create plausible 3D objects, with Prolific Dreamer showing semantic coherence but with issues like Janus problems, where the back is mistakenly optimized as another front. GS-Gen improves 3D consistency by incorporating 3D priors, although texture fidelity remains underwhelming. MVDream addresses multi-view inconsistency better by using multi-view images rendered from 3D data, but it struggles with cartoon-style textures and maintaining semantic accuracy, especially with challenging prompts. Quantitative comparison. Table 2 outlines a quantitative evaluation of the models based on generation quality, text-image consistency, and 3D consistency. The metrics used are FID clip lower is better, clip R-score, Uni 3D score higher is better, and cons rate, which indicates the success rate in avoiding 3D or semantic inconsistencies. The author's method outperforms the other three across all metrics, suggesting it achieves high fidelity, text image, and text 3D consistency while retaining 3D spatial consistency. The text also notes that the author's method, likely called GeoDream based on context, adds explicit 3D priors to a 2D diffusion model, resulting in generated 3D assets that are both photorealistic in texture details and semantically coherent. These results can be seen in Figure 1 and Figure 3, with further analysis and comparisons provided in supplementary material. The given text is an excerpt from a research paper discussing an ablation study on the proposed improvements of a system named GeoDream, which is used for text-to-3D generation. The study aims to justify the effectiveness of different design decisions in the system. Summary. The study examines the importance of using 3D priors. Initial visualization showed that geometric cues could help with the 3D consistency in 2D diffusion models, reducing issues like multifaceted appearances. The authors suggest using optimizable, evolving 3D priors instead of fixed ones, which results in progressively refined outcomes. Without 3D priors, randomly initializing, issues with 3D inconsistency can arise. The study also evaluates the learning rate decay schedule for the cost volume. It is found that starting with a lower learning rate for the cost volume and gradually increasing it helps optimize geometric details, while doing the opposite for the texture learning rate prevents content drift at later stages. The effect of texture priors was examined, revealing that introducing such priors could lead to non-photorealistic and over-smoothed appearances. This suggests the importance of relying only on 3D geometric priors to avoid compromising appearance modeling. Mesh fine-tuning is discussed, converting US to DM Tate to enhance geometric and appearance details. This conversion produces better results with improved 3D consistency and surface accuracy. The impact of rendering resolution is addressed, showing that integrating 3D geometric priors allowed the researchers to increase rendering resolution from 512 to 1024 with improved optimization and better results. GeoDream also manages to provide competitive results at a 512 resolution. Finally, the researchers conclude that by using these improved methods, they can render higher fidelity images and better detailed texture meshes, while significantly reducing common problems associated with 3D generation, like the Janus effect, two-faced inconsistency in models. The text discusses a method that enhances the performance of 2D diffusion processes by incorporating 3D geometric cues into a disentangled solution. The disentangled approach allows for the gradual optimization of 3D priors. Visual and numerical comparisons with current leading methods demonstrate the effectiveness of this strategy and indicate its superiority in generating 3D content. The supplementary material for GeoDream, Disentangling 2D and Geometric Priors for High Fidelity and Consistent 3D Generation, includes a video that provides additional visualizations for a better understanding of the content. The source code and 3D metric are available to support future research. The text explains the Janus problem, which is the issue of 3D inconsistency, where generated 3D models display multiple canonical views instead of a desired output that would reflect a coherent 3D object. This problem is prominent in models of asymmetric objects, such as people or animals, but less so in symmetric objects. More visual comparisons with other 3D generation methods like Fantasia 3D, Wonder 3D, and Magic 123 are presented. The comparison highlights the advantages of using geometry initialization with 3D priors and the benefits of disentangling 3D and 2D priors to achieve high-fidelity and semantically coherent 3D assets without geometric or textural distortions. A viewpoint sampling strategy is proposed to enhance the stability of constructing cost volumes for more accurate multi-view models. This strategy involves using front and side views for reference and addresses the inadequacies of back-view predictions by multi-view diffusion models. Specific methods for obtaining reference views are described, including using stable diffusion and GeoDream, with different strategies for sampling viewpoints based on the reference views obtained. The goal is to mitigate inconsistencies and improve the accuracy of predicting non-canonical views. The text appears to be an excerpt from an academic or technical paper discussing advancements in 3D visualization and rendering techniques. The summary, based on the provided section, the document discusses visualization comparisons between the proposed method and baseline methods for generating 3D assets using prompts such as a statue of an astronaut, a stylized little building, a colorful mushroom on a log, and an ice cream cone. It details how learning rates are scheduled differently for cost volume and texture in the 3D model construction process, with an emphasis on maintaining geometric cues early on and preventing content drift later in the optimization stage. As depicted in Figure 6, a strategy to improve 3D rendering quality by incorporating viewpoint sampling is introduced. This strategy improves the consistency and quality of the 3D models when using reference views predicted by both Stable Diffusion and GeoDream. Despite some roughness in the cost volume due to inconsistencies between source views, the final 3D assets exhibit rich detail and consistent geometry, suggesting that disentangling 3D and 2D priors could be a promising research direction for refining 3D models while leveraging 2D diffusion priors. Furthermore, the paper describes a proposed learning rate decay schedule that begins with a lower rate for cost volume to enhance geometric detail and a higher rate for texture to combat early overfitting. Lastly, a section on ablation studies is briefly mentioned, which covers negative prompting, rendering resolution, and addressing corner case prompting. Utilizing a technique called perp-neg, that converts 2D diffusion models into 3D and addresses a problem named the Janus problem. The paper suggests integrating this negative prompt algorithm into systems named Prolific Dreamer and Geo. Please note that the text is incomplete, and thus the summary is based only on the available content. The text discusses an analysis of the performance of GeoDream, a method for generating 3D assets from text prompts. The focus is on comparing reference views obtained from text prompts using two systems, Stable Diffusion and GeoDream. The research demonstrates that GeoDream adapts to reference views from different sources effectively. Specifically, the document addresses the following points. 1. Comparison. It compares the 3D assets generated from predicted reference views by Stable Diffusion and GeoDream. For example, it gives reference to assets like a majestic giraffe with a long neck and a Viking axe in high resolution. 2. Negative prompt algorithm. The research looked at a negative prompt algorithm, which was found to be ineffective at solving an issue referred to as the Janus problem. Consequently, they decided not to use this algorithm by default. 3. Rendering resolution. An attempt to increase rendering resolution to 2024 exposed oversaturation issues and collapsed geometry in the Prolific Dreamer system. 4. Corner cases. GeoDream handles corner cases better than multi-view diffusion techniques, especially where the spatial relationship between objects is complex. For example, a squirrel playing a guitar, as 3D training data is sparse. 5. Training stability and diversity. GeoDream is found to have exceptional stability during training, attributed to the 3D priors it introduces, which minimize randomness. Additionally, GeoDream can generate a diverse range of 3D models by exploiting the diversity in the Stable Diffusion and GeoDream systems. In summary, the research indicates that GeoDream is both stable and capable of generating diverse and semantically correct 3D assets from text prompts, adapting well to different reference view sources and demonstrating resilience in complex scenarios.